Decision tree classifiers. We can use the decision-making process to make decision trees that are predictive models. They're highly intuitive, but they're also possibly unstable, biased, they're strictly linear, and they do tend to overfit the data. So predictive models in big data often rely on networks, maybe nodes as observations, edges as association, applicable to structured and unstructured, applicable to supervised and unsupervised. But the vertices are also very important. It's not just all edges. The vertices aren't just dots where edges come together. Decisions are made at vertices. Processes are implemented at vertices. In fact, much of the rest of this course is devoted to what happens at the vertices of a network model. So let's look at binary classifiers. They're going to be very important for us. Often we'll use this notation, positives and negatives, and we'll have P as the number of positives, N as the number of negatives. We'll have two possible predictions, either positive or negative. Little p is the number of observations classified as positive, little n the number of observations classified as negative. Sometimes we'll use 1 for positives and 0 for negatives. We've already seen that. So decision tree classifiers are based on information gain at the nodes. They're defined recursively. We partition at the previous level, we get populations at the next level, and we do it again. So we start with a condition, then we get more conditions, and we keep going. We're going to use information gain. Our goal is actually purity. It would be nice if we could find a condition which split the data into pure negatives and positives. So information gain is interpreted often as a measure of impurity. There are also other measures of impurity we'll see later. So let's look at the iris data. There's 3 classes, I setosa, I versicolor, and I virginica. 4 features, petal width and length, sepal width and length. In sklearn, the scikit-learn package, it will look something like this. We have an algorithm object, in this case a classifier. We'll fit it to the data, and then we'll have the ability to do analysis and visualization and that sort of thing. Notice there's a lot of options here. We just used what was given. Here's the result. It's a decision tree. Notice that we have these conditions and we end with these leaves where things are described. There are, in fact, an awful lot of options. Here we have a max depth of 2. So that means the decision tree wasn't allowed to get more than 2 levels deep. We can also use different measures of impurity. Here is the decision tree you get with the Gini impurity. It's a fairly simple idea. This product measures impurity, and we want to minimize total impurity. Here's another example. We have a min sample split of 10. So notice that anytime you get below 10 for the number of samples, you're forced to stop. Okay. Of course, we stopped here because that was very pure. So how to choose modules options is in the next module. Right now, we're just going to focus on the trees. To do so, we need to consider a more intuitive set of data. The iris data is not necessarily something people are that familiar with, but everybody's familiar with getting dessert. So you've got 111 restaurant patrons. Can we train a decision tree to predict who's going to get dessert? There's a lot of conditions to consider. So what are they going to be drinking? What's their entree? Did they get an appetizer? Only 35 of the 111 get dessert, so we can compute the classifier entropy, the capital Y, as just the standard definition of entropy, and that's 0.8992 bits. And so this is the largest possible information gain we could get from a condition. So let's start with gender. So if the gender is female, from that we get 0.8990 bits for the entropy, and the information gain is therefore 2/10,000ths of a bit. That's not very much. Whether or not they're an adult, we get a little more information, but not much. Now, when we get to the beverages, notice they could be doing water, which would be beverage equal water, true or false, beverage equal tea, true or false, beverage equal soda, true or false. And notice that when we have beverage equals soda, true or false, we get 0.02. This is the highest so far. Well, let's keep going. Appetizer, we haven't passed our highest so far. Whether or not we got a salad, there again, haven't reached as far up as the 0.02 with the beverage equals soda. And finally, the entree is still going to give us a highest for the beverage. The entree's information gain is just 0.02 versus 0.021. So now we start our decision tree. Our first condition is going to be beverage equals soda, and that's either true or false. So we split the population, and we are next going to look at the 26 that are true for the soda, and then we'll look at the 85 that are false for the soda. So on the true side, turns out the next condition we'll look at is whether or not they get an appetizer, and then whether or not they got fish or ate a vegetarian. And those who did get fish or a vegetarian, we'll look at whether they got a salad. If they didn't get a fish or vegetarian, 13 of those did not get dessert, and 0 of those did. So we'll stop there. We can't do any better than that. That's pure. But we'll keep going, and eventually we'll have to go to the other side and so on. And here's the result. So this is the actual tree, and you can see where you can track down through there. We had this one on the other side, but you can see it's flipped, but it's essentially the same tree that we were starting. Now, this is actually produced by a program called Rattle, and this is using the statistical language R. I'm going to illustrate some of the trees using Rattle just because it's a nice package. I've always liked Rattle, use it a lot. It can't do everything I need to do, but it can do a lot. So now we can ask the question, is he getting dessert? So suppose we have an adult male who drinks tea, gets an appetizer and a salad, and orders beef. Is he getting dessert? Well, let's find out. So we start out with, is he getting dessert? He's a male adult, and his beverage is tea, so we start with the beverage being equal to tea. And that takes us to whether or not he got an appetizer. And he did get an appetizer. So then whether or not he got beef, and he did get beef. And so we predict that no, he's not going to get dessert. What about her? Is she going to get dessert? Once again, we start with with beverage, and she got a soda. So now we're going to be in this direction, and then the gender is female, and then she did get the beef, and she didn't get the dessert. We predict she's not getting dessert. So in summary, information gain can be used to construct decision tree classifiers. Classification via a sequence of conditions, and the decisions are applications of those conditions. Now, we haven't gotten into it, but we actually trained this using a training set and then applied it to test data and actually used validation. And we'll look at that in the next module when we talk about metrics.